So now that we have looked at exponential functions and how to solve them, we want to look at how they apply to some of the things that we might see in real life. So we're going to look at a couple examples here of different exponential functions. Okay. First one that we're going to look at here is called Newton's law of cooling. Now, the main thing that we want to be able to do in all of these exponential functions that we're going to look at is be able to reading a situation. We want to be able to plug into our formulas and solve for whatever variable that they're looking at. So let's look at this first problem, this first example. Here it says an object is heated to 100 degrees Celsius and is then allowed to cool in a room whose air temperature is 30 degrees Celsius. The first question says, if the temperature of the object is 80 degrees Celsius after 5 minutes, when will its temperature be 50 degrees Celsius? So let's kind of try to label what we know, try to figure out what we can plug into our equation, and then go from there. So one of the things that I notice is that this is going to be a two-step problem. The reason I know this is because I'm given two types of temperatures here at the end, 80 and 50. Okay, so I can't plug both of those into the same exact spot, which means that one of them must be used to find my K or my constant, and then used in my second equation. Okay, so let's kind of explore what that means. All right, so my first equation, first thing that we know in general is that 30 is going to get plugged in to my capital T here. Okay, 100 is going to get plugged into my initial. 5 is going to get plugged into my time, my T. And 80 is what I'm going to be equal to. So let's start plugging in. We've got our 80 is going to equal 30 plus 100 minus 30 e to the k times 5. All right? So we're going to solve this for k. So we're going to have to use all of our solving of exponential functions that we've looked at so far. Once we figure out what k is, then we will create a second equation where we'll go plug in 50 to find our actual final answer. Okay, so first thing we want to do is we want to solve this equation here. So I know that 100 minus 30 is just 70. I'm going to subtract this 30 to both sides. So it's going to give me 50 equals 70 e to the, I'm just going to say 5k. Most of the time we put our number in front of our variable, right? Now what I'm going to do, I'm going to continue to isolate that exponent. Remember that was our way to solve. Isolate the exponent, get rid of our base by changing it into a log, and then continue to solve. Remember we did that in the last section. So we're going to continue on that. I'm going to divide it by 70. So I'm going to get 0.71, and again that's rounded, e to the 5k. Now to get rid of my base, my e, I'm going to change it into a log. Remember the log with a base e is going to be my natural log. So I'm going to natural log 0.71 equals 5k. Okay. Then what I'm going to do is I'm going to divide that number by 5. Now I like to wait until the very end to actually type it in, so then it's not as rounded. Okay, so I'm going to go plug all this part into my calculator now, and it's going to give me negative 0.068. Normally we're around to say the hundredths or the thousandths place, all right? So using this, I can go back and I can solve knowing that 50 is now the temperature that I'm trying to get to. All right. So all I'm going to do is I'm going to go back. I'm going to use the same exact type of solving that I just did, except for instead of using my 80 here, I'm going to be using my 50. So let's set that equation up. I'm going to say 50 equals 30 plus 100 minus 30. And yes, we already know what that is, but we'll just write it down. I'm going to use the K that I just found. Okay, so I'm going to have negative 0.068 times my T. Right? And this time I'm solving for when, so I'm solving for that T. Okay, so I will literally do the same exact process that I just did. I'm going to move the 30, divide by the 70, take my natural log, and then divide by that negative 0.068. Okay, so let's do it. I'm going to subtract my 30. Right, we remember that that was just a 70. I'm going to divide by my 70. Again, I'm rounding, so it's going to be about 0.29 e to the negative 0.068 t. Now to get rid of that e, I'm going to introduce my natural log. So I'm going to natural log that 0.29. Then I'm going to divide it by that negative 0.068. Again, I'm going to wait until now to go to my calculator, plug that in, and I'll figure out what the time is. So plugging all that in, I get about 18.2 minutes. Okay, and again, we may have rounded differently throughout, so it might be a little bit off, but I should have somewhere around 18 minutes. If you're following with my exact decimals, that's what I typed into my calculator. All right. In my math lab, you want to make sure that you're using whatever decimals that they are asking you to use. Okay. On, say, the test or the exam, they would tell you what to round to, or you could look at the answer choices, but there's not going to be two answers that are super close. Like there wouldn't be one that's like 18.2 and one that's 18.5. It might be 18 and 23. So of course those would be vastly different. So there's no way I could be that far off. Okay. So I don't want you to get too worried about that. All right. So now that we've done part A, let's look at part B. It says determine the elapsed time before the temperature of the object is 35. Now, remember this K is a constant. So once we have found K, that is what we will always use. Just like we're always going back and we're using that 100 is our mu, our 30 is our T. Now we also have that our K is this negative 0.068 because it's a constant. So all I'm going to do in this problem, same thing like last time, I'm going to use that 35 in place of the 80, in place of the 50, right? I'm just going to plug it in and figure out the time, find my T. So let's do it. I'm going to say 35 equals 30 plus 100 minus 30 e to the negative 0.068 t. All right. Solving this, I'm going to subtract that 30. Remember, this is just 70. I'm going to divide by that 70. Again, I'm rounding to 0.071 e to the negative 0.068t. To get rid of that e, I'm going to introduce my natural log. Okay, I'm going to come down here, see if we can follow here. So I'll just rewrite that last step that I was doing. Add that e to the negative 0.068t. And I'm going to introduce a natural log here. So I'm going to natural log that 0.071. Then I'm going to divide by that negative 0.068. And I can find my t to be about 38.9. And this is going to be minutes. Okay. So, again, if I'm not exactly that amount, that's fine. If you're using that rounded number that I'm using all the way through, then you should get that exact value. Okay. So one application that we looked at is that Newton's law of cooling. The next set of applications that we want to look at is going to be our growth and our decay. Okay, they call it uninhibited growth and uninhibited decay. So we've kind of got a graph here. What I should notice is it's the same type of growth and decay that we looked at when we looked at a basic exponential function. All right, so what we used to use when we were graphing, we said that we would have an initial amount and then we had a base. In this case, our base will always be an e, okay? And then we were going to raise it to a variable, okay? All we're doing now is we're going to expand that. Our initial is considered our a naught. We're going to be using our e, and the variable that we're going to raise it to now is an element of two things. It's the constant rate times time. All right, so it's very similar to what you've already seen before, and we used to call it y equals. It's the same idea here. Okay, so when we look at growth, we would be seeing when our exponent here is going to be greater than 0, right? We looked at this before. Growth is where k is greater than 0, a positive number. It's increasing. And decay would be whenever we had k being less than 0, or it's going to be decreasing. So we're going to look at an example of each of these, all right? When we look at growth, same idea. K is greater than 0. When we look at decay, k is less than 0. It does not matter what letters that they use. Okay, so in this first one, they're using N for the number of cells. In our last one, they're going to be using A for radioactive. It does not matter what letter that they're using. All I know is that I'm going to have an initial amount, then I'm going to have my number E, which is going to represent my base, and it's going to be raised to a rate times a time. If it's growth, that rate is going to be positive. If it's decay, that constant will be negative. All right, so let's look at our first one here. Okay, it says a colony of bacteria that grows according to the law of uninhibited growth is modeled by the function in n of t equals 100 e to the 0.045 t, where n is measured in grams and t is measured in days. So the first thing that they want us to do is just determine what is the initial amount. Now I remember the formula, and my formula says that the number in front of my E base is the initial, so it's going to be 100 grams. All right. Then it says, what is the growth rate? So remember, K is going to represent my growth rate. And it's growth because it's greater than 0. So I could say 0.045. Then it says, what is the population after 5 days? So now they're giving me a time to go plug in to this t. So let's do a little math here. We've got 100 e to the 0.045, and then they're telling me to plug in 5 days. All right? This I can go straight to my calculator, plug it in, and I would get 125.23. Okay, and this would be in grams. Okay. Then it says, let me write that over here. Then it says they want to know how long will it take to reach 140. So this time they want to find what the t is, and they're giving me what it's equal to. All right. So this time I'm going to say 140 equals 100 e to the 0.045 t. This is going to be just like how we solved our problem in the last examples. There's no number to subtract over, so the first thing I'm going to do here is I'm going to divide. So I'm going to divide by my 100. Then to get rid of that e, I'm going to introduce my natural log. So I'm going to do natural log of 1.4 equals 0.045t. Then I'd be dividing by that 0.045. Remember, I'm going to wait until now, and I'm going to go plug all of that in. And so I would find that t is going to equal 7.48. Again, that's rounded, and this is measured in days. Okay. So the last question asks me, what is the doubling time for the population? So you're thinking, well, I probably can't do this when they didn't give me enough information, but they did. If I want to know the doubling time, so first off, I'm looking for t, and I know that it has now doubled. So if the initial was 100, that means doubled should equal 200. So they might not give me the number to plug in. They might tell me it's doubled, it's tripled, it's quadrupled, it's half, right? So I can plug in just by looking at what that initial is. Okay, so it's doubled, so I can now plug in a 200 there, e to the 0.045 t. So it's actually going to be solved exactly like what we just did here a moment ago. All right. So the first thing that I'm going to go do is I'm going to divide by that 100, which I should get 2 because it's been doubled, right? So doubling here means I should equal 2. So could I skip that step? Sure, but if that is like, what do you mean skip a step? Then don't, okay? So now I'm going to get rid of that e by introducing a natural log. So I'm going to natural log 2 equals 0.045 t. Then I'm going to divide by 0.045. So I'm going to get t is going to equal 15.4 days. All right, so now we have seen how to identify all the different elements. Where is our initial? Where is our constant? How do we solve for the final amount? How do we solve for the time, right? All of those different things. We know that it was growth because it was a positive constant. So now what we want to do is let's do the same thing but looking at a decay. So the only difference here is that my constant should be negative. I'm going to solve everything else the same way. I'm going to be able to identify where the initial is, the final amount, the constant, the time, everything. The placement is the same. It's just that constant is a negative instead of a positive. All right. So let's look at this example. They say traces of burned wood along the ancient stone tools in an archaeological dig in Chile were found to contain approximately 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,730 years, approximately when was the tree cut and burned? All right, so let's identify kind of what we know here. So the first thing that I want to look at is this idea of half-life that they're talking about. So a half-life means, just like when we were talking about doubling, if I know the initial, I could cut it in half and then I would know what the final amount is. So honestly, it does not matter what the initial is at this current moment. So let's just say we're going to use our initial amount to be 100. Does not matter at the current moment. So initial amount we're going to use to equal 100. So if I have 100 as my initial, the half-life, that means half of it would be 50. Okay? And it's saying that the half-life occurred in 5,730 years. So I'm going to use my K, 5,730 years. Okay? The reason I want to use this is so that I can find that K, that constant, similar to how we did in the very first example with that Newton's law of cooling. I want to find what K is so that I can continue to use that over and over because it is a constant. So whatever it is in one scenario will be that way through all of them. All right, so let's find out what K is. So same way that we were solving last time, first thing I want to do is I want to divide by that 100, which we know it's a half-life, so it should equal 1/2. Okay, 5,730 K. So to get rid of that E, I'm going to introduce that natural log. And then I'm going to divide by that 5,730. Before I actually go to my calculator, I want to divide it, okay? So dividing by that 5,730, we're going to get K to equal negative 0.00012. All right, so now that I found what K is, I can use that constant for any other problem, okay? Now, let's go back and it says approximately 1.67% of the original amount. So what I could do here is I could say, well, if we knew the initial amount and we had half of it, which would have been 50% of the original amount, then we knew that it was going to be equal to 50. So I could do the same idea. I could say 100 as my initial amount. And if I wanted to take 1.6% or 1.67% of the original amount, then I would end up with 167. All right, so I'm going to set that equal. I'm going to use my rate that we just found. My first step is going to be divide by that 100, which I should get that 1.67 that we were looking for, right? If I don't, then I need to go back and fix. Oh, I forgot my T up there. Sorry about that. Okay. Now to get rid of the E, I'm going to introduce that natural log. And divide by that negative 0.00012. Right? Doing that, I would get the time to equal somewhere around 4,273.53 years. Now you might be asking yourself, well, wait a second, I got a negative in my calculator. I should, because that's how many years ago that it happened. But I wouldn't say, oh, it was a negative 4,273.53 years. I would say it was that many years ago. So now we've looked at a couple different ways to apply those exponential functions and equations that we had looked at in the previous section. All right. When we look at exponential functions, we're typically going to look at exponential growths, exponential decays, and then we kind of threw in an extra one about that Newton's law of cooling. They might give me a completely different equation that they want me to analyze. I can analyze knowing if it's growth or decay by looking at the constant. Is it positive? Is it negative? I would be able to find where the initial is by looking at what number is being multiplied in front. So there's lots of different ways that we can apply this idea of an exponential function in the real world.